Hello, welcome to today's video where we're going to look at how to resolve vectors, which is a useful skill as part of some mechanics problems. But what do we actually mean by that? Well, I'm hoping you're already familiar with the idea of resolving things from before in other areas of mechanics, most commonly probably resolving forces, because something we used to like to sometimes try to do is to take a diagonal force and then find out how much of that is taking effect in the horizontal directions and the vertical directions. And we did that by resolving using trigonometry and a triangle. For instance, the horizontal component of this 7 Newton diagonal force would be 7 cos alpha, and then the vertical component of this force by trigonometry would be 7 sine alpha. But what happens if we aren't given a scalar quantity? In other words, what happens if the thing we're trying to resolve isn't just a single number? What happens if instead it's a vector? Well, if we're still trying to resolve horizontally and vertically, probably not much of an issue, because if we assume that the I component is taken to be the right-hand direction in 2 dimensions, which it usually is, then therefore the base of our triangle would just be 1, and the vertical component of our triangle would just be the j component, as that's usually taken to be the upwards direction in 2D, so that would therefore be a 2. In other words, we're just literally reading off the 2 components of the vector, nice and easy. But what happens if we're not trying to resolve horizontally and vertically? And even worse, we're not given an angle, and instead we're just told a vector that we're trying to resolve in the direction of, or parallel to. Well, therefore that is what we are trying to look at today. In other words, something fairly similar to what we were already dealing with before, with forces, but now we're dealing with vectors in the problem rather than just single numbers and angles in a triangle. It's worth noting that there are, in reality, lots of different ways you could approach this problem, and some students don't really ever bother to learn a set method for doing this stuff and just find their way to the answer using geometrical problem solving skills. Which is fine, but I'm hoping after watching this video you see the benefits of taking the approach that we're going to be showing here today. However, in order to do the method we're doing today, you need to know the vectors of all the directions you're trying to resolve in. And as we often like to be able to resolve both parallel and perpendicular to something in mechanics, that's a bit of a problem here, because we've only been given one of the directions that we need to be able to resolve in. So therefore it would be good to know the direction of this side of the triangle if this is what we are trying to resolve. As this side of the triangle is perpendicular to the other side of the triangle down here, this means we need to know how to find a vector that's perpendicular to another vector in 2D. So therefore, that's what we're going to start with. So how do you find a vector that's perpendicular to another? Well, there's 2 main approaches I'm going to show you here to explain that. One way to think about this is to link what we're doing with vectors back to what's going on with gradients. For instance, the vector 3, 4 could be viewed as something that's going 3 to the right and 4 up. And therefore, we could work out the gradient because gradients just change in y over change in x. So therefore, the gradient for this would be viewed as just 4/3. You should also be aware that a perpendicular gradient is always just a negative reciprocal, so the perpendicular gradient to this would just be minus 3/4, or minus 3/4 you could view it. So what you might notice is we've taken the 2 numbers in the fractions, switched them around, and multiplied one of them by -1. So the same thing can be done to a vector. If you have the vector 3, 4, all you have to do to find a vector that's perpendicular to it is swap the components around and multiply one of the components by -1. So in this case, I've chosen the vector -4, 3. Cool. That's one way of looking at it. Another alternative way of looking at it is, hopefully by now you've come across in vectors something called the cross product. The cross product is a way of taking 2 3D vectors and then finding a third vector that's perpendicular to both of them. Now in this case that's a bit weird to think about because we don't have 2 vectors, we've only got one, and it's a vector in 2D rather than a vector in 3D. But therefore we could apply a similar approach as to what we do with a cross product between 2 vectors to apply it to just a single vector in 2D. We could just do the determinant of a matrix, which has got the first row as ij and the second row as the vector we're trying to find the perpendicular vector for. So therefore if you do that, we'll end up with 4i minus 3j. And so therefore that's another alternative vector that is perpendicular to 3, 4. either of the two methods I've just shown here are valid and would work for finding a vector that's perpendicular to your vector in 2 dimensions. So, okay, now we know both of the directions we're trying to resolve in, but how do you actually resolve vectors? Well, to do it, I'm unfortunately going to have to break one of my own rules, controversially, that I've abided to up until now when doing any vectors content, which is that I've always tried to avoid using any formulas which aren't directly given to you in the formula booklet. And that's because although there are ultimately formulas that you can use for almost any of the vectors content for dealing with all the specific scenarios involving lines and planes, etc., I've always felt that if you have to remember 50 billion different formulas, or what feels like it at least, then that makes things a lot more difficult because you have to sit there learning by rote for ages all of these things before you go into an exam. Whereas if you can just solve things geometrically using problem solving skills, it's a lot more intuitive. However, I am going to use a formula today, and hopefully when you see the formula, you'll see why I feel that it's actually worth remembering, because it's such a simple formula, it's a lot easier to remember than some of the other formulas, which have a lot more different parts involved, which makes them more tricky to remember. So, if we're resolving the vector A in the direction of a vector B, then that is just going to equal A dot B over B dot B lots of B. So yes, that is the formula we're using, and the reason I like it is partly because the way you read the formula is similar to how you're reading or saying what it is you're trying to do. We're trying to resolve the vector A in the direction of B, so therefore in the formula I'm saying A dot, and then you're just saying B lots of times. A dot B over B dot B lots of B. There is a lot of the letter B in that formula, and that's why I can remember it, because it's so simple. So that is all there is to it. The fraction part of it is just telling you how much of the vector B we need once we've done the resolving. So let's get on and do an example. So we want to resolve the vector I showed earlier, which was the vector 1, 2, firstly in the direction of 3, 4, so parallel to 3, 4, and then we want to resolve 1, 2 in the direction perpendicular to 3, 4. As we already said earlier, we need to know what that direction is. So that's why I showed you how to find a vector perpendicular to a given vector. And we already decided earlier that a vector that's perpendicular to that could be minus 4, 3, or alternatively 4, minus 3 if you prefer. It wouldn't matter. That's the thing about the method we're doing. It will all work out the same in the end, even though the method will look slightly different depending on where your minus sign was placed. So let's do part A. All you've got to do genuinely is to do the vector we're trying to resolve, 1, 2, dotted with the vector we're trying to resolve in the direction of, so 3, 4, and then divide by 3, 4 dot 3, 4, and that's going to be telling us how much of the vector 3, 4 we need. So now we've just got to work out what that is. Oh yeah, I forgot to indicate this is part A. So doing that dot product is really quick. So 3 times by 1 is 3, plus 2 times by 4, which is 8. That's the top of the fraction done. On the bottom of the fraction, 3 times 3 is 9, 4 times by 4 is 16. So therefore, that's how much we've got of the vector 3, 4. And that's just going to simplify to 11 over 25, lots of the vector 3, 4. Now, because that number out the front is a scalar, you could then choose to go on and multiply the individual components inside that vector by that number out the front, but I don't bother because, hey, that just takes more writing. So we've got what we needed. This is how much you get when you resolve the vector 1, 2 in the direction of 3, 4. We're now going to do the same thing for the part B, but now we're resolving 1, 2 in the direction minus 4, 3. So therefore we're going to do 1, 2 dotted with minus 4, 3 divided by minus 4, 3 dotted with minus 4, 3. Lots of minus 4, 3. So we just got to continue on and work that out. So the top will now be minus 4 plus 2 times by 3, which is 6. And here's the interesting thing about the bottom. Although you could manually work out what the bottom of this fraction is again using these two vectors of minus 4, 3, minus 4, 3, although these are a different vector to what we had on the denominator previously, just because of the way the numbers work with 2D vectors, this perpendicular vector we've now got dotted with itself will come to the same result as the vector we had before dotted with itself. So therefore I already know the denominator of this fraction will be 25 because I'd worked out the denominator to be 25 previously. And then therefore this is how many lots of minus 4, 3 we're now going to have. So therefore we have as a final answer 2/25 lots of minus 4, 3. So therefore we've now resolved 1, 2 in the direction minus 4, 3, and therefore that's the resolving done, ready for you to do whatever it is you're trying to do with this vector. Now for those of you wondering if what we've just done is legitimate, there is a way you can check your answer to see if what you've done actually makes sense, which is that when we've split up our original vector into these two components, they're not components just in the directions of the unit vectors I and j, but they're still components of the original vector. Basically, our two resolved vectors should add up to make the original vector we had. So 11/25, 3, 4 plus 2/25 minus 4, 3 should add up together to make the original vector of 1, 2 again. If it doesn't, you know you've done some sort of mistake when doing the resolving, but if it does, it shows that it all worked fine. So there you go. That's how you resolve vectors, and it's just using that formula. Sometimes called, by the way, the projection of a vector onto another vector formula. And it's worth pointing out there is a proof for that formula that I will do a video on at some point in the future. If you're watching this video far into the future, maybe I've made that video, and in which case, if that is the case, the link to that video will now appear on the screen right now. But if not, see you in a future mechanics video where we'll be using this skill to help us solve some mechanics problems. Okay, goodbye.